I'm very pleased to be here at the European Test Symposium, premier scientific conference of the international test community. And what a coincidence. It is held in Venice, one of the most significant state cities of the Italian Renaissance. And at the same time, the semiconductor industry is going into what we could call Renaissance, not only because of the technologies that are developed, they're really fascinating, but also the funding that is assigned. That is the US Chip Act and the European US Chip and Science Act and the European Chip Act, aimed at developing scale and innovation in semiconductors, which is really great news for this community. Important to emphasize that DFT has been playing a key role in the digital revolution. And I think if anything, DFT has even bigger role to play in the future. And this is what is the topic, the direction of my talk. And I have seen a lot of keynote speeches and gave a couple of them myself. And I know that there are two possible outcomes. People will either forget what you said, this will be very unfortunate, or people will remember. Now you have to be careful how much risk you want to take, because if you prognosticate about something and it doesn't happen, or happen just something opposite, then your professional credibility could suffer tremendously, and you will never be invited to give a keynote speech, right? On the other hand, if you're lucky, you really have to be lucky, and you guess what might happen, then that'll be fine. So the DFT will play much bigger role. It will evolve, as it has done many times in the past. It will evolve to tackle new challenges, mobilize the community. People will invent things and move things forward. Now, when you think about the responsibility that we have as a community by researching, developing, and putting together a whole DFT solution for the semiconductor industry, it is pretty significant responsibility. You have to really think ahead as long as you can. In our case, we very often look 5 to 10 years ahead, just to make sure that we look at all the sources of information. So once we come up with something, it will actually have the expected longevity, so that the industry that adopts it will not have to backtrack and do something else. And there are really three important things that, in my view, you have to consider when you think about the technology roadmap for DFT. And silicon lifecycle management, for me, is just another phase, another step of evolution of DFT. So the three important things that you have to consider are, you really have to understand the technology, like the technology node. You have to understand how the transistors are built, what is their defectivity, how to diagnose them, and so on. So this is like the low level of detail, the lowest that you have to get to really understand the impact. Now, the other aspect is the design. Okay, so how a chip looks like, because not only you have to understand the defects, but also how to detect them in context of SoC. And the third level is the system level functions that are impacted by DFT or are relevant for DFT. And then when you think about the whole picture, then you would like to come up with DFT solution that could be utilized, could be used through all phases, from design through manufacturing, all the way to a system. All right, so let's talk about the three different challenges that we have to somehow understand and put together to come up with a vision. And what I really will talk today is the future of DFT and test and future of lifecycle management, how those things will interact. So let's start with technology. Today's technology is, well, it's technology of the day. We would like to say that it's complex, but it was always complex. As far as we can think back, it was always state of the art, which means that the technology, we could barely make it to work. Okay, that's the definition of state of the art. Okay, there's a number of manufacturing steps. We have also FinFET and nanosheet transistors. The lithography is pretty complex because we're using multiple patterning in lithography, and those phenomena introduce new types of defects. In the past, we worried about a clean room technology, and the defects that we used in the past were derivative of that concern. Today, defects are more complex. Okay, there's more parametric defects. The feature sizes are so small that if we have just minimal misalignment that in the past wouldn't really cause anything, it may cause actually systematic issues. Okay, there's also susceptibility to aging, which we didn't have in all the technologies because they were more robust. The newer technologies are very, you could say, fragile. So aging is an issue. And all of you heard about silent data corruption errors reported by several mega data centers, operators of those centers, and so on. So it's difficult to be anybody in DFT without hearing about those things. It is important because when I talk to some of my friends from the semiconductor industry, they say that quality of test is right now probably #1 issue, at least in certain market segments, to a point that it could impact competitive landscape. If one company supplying, let's say, chips to mega data centers will develop technology to drastically reduce early mortality, test escapes, things like those, then it could win competitively, which is a very interesting thing to observe, because that means that the other companies are also looking at new technologies. So for us, it is opportunity, but also pressure to develop those technologies. All right. Now, these are some of the things that I mentioned. So, so the guys that operate large mega data centers, and by large mega data center, we consider anything that has more than 15,000 servers. The server can have 120 something cores. Okay. Bigger data centers that may have 100,000 servers. Some of them have like million square feet and consume 100 megawatts of power. The bigger ones have 10 million square feet, close to 1 gigawatt of power. So if something happens there, there is a delay, the costs are enormous. There's some data that I'm not even going to quote here because I still have difficulties in understanding that a second of delay in response time when somebody is browsing and looking to buy something on internet, the cost of it in sale is tremendous. It's tremendous. You can search it yourself. So there's a lot of pressure to build those systems in a very, so that they can operate in a very reliable way, right? Now, I've been around for a while. And this is probably the first time that I saw that major national newspaper like the New York Times is concerned about reliability of chips that go to data centers. Okay. And I lived through those days that there were even discussions that scan is overhead. Can you imagine that? Luckily, we're past that. Now we learn that any wise investment in DFT is actually tremendous ROI, because we can gain a lot of things in cost of development, quality. I mean, the gains are just spectacular. Okay, so these statements are very important. They're consequential, because what that means is that the other industry react to this message, and they do something about it because they see opportunities. Okay, they see a world. But the other side of the coin is that it's also indicative that those companies that tell us about those problems, they are willing to make trade-offs. And this is typically a moment that you see there is a discontinuity. Companies are willing to make different trade-offs, more global trade-offs. They are willing to invest in something to make even bigger gains, which is actually good. So design. So now that we can produce dies that have 100 billion transistors, the question is how the designer is going to use such capacity. Well, what typically happens is that the designer will design something that requires 200 billion transistors and will use multi-die to implement it. Isn't that interesting? Okay. So now designs are not only complex like big, but they're qualitatively different because they're using features like dynamic voltage scaling. In the design process, they have to make sure that those designs are very robust. They work under various environmental conditions, and they also tolerate process variability. Okay, and on the test side, we need to understand that because there is an opportunity to improve things, and I'll show you how. That's how I usually give keynote speeches. I don't only tell you there's a problem, there's a problem. I'm tempted to look at what are the solutions. All right. So the other aspect is the system level stuff. So how this chip or multi-die design is going to be used. Okay, what is expected from the end user, not just the designer, but the end user, like, for example, the data center operator. Okay, so reliability is very important. There's also silicon aging, especially in the newest, smallest technology nodes. There was not such an issue for older technologies, but when you get to FinFET and gate all around and so on, it is becoming an important issue. Okay. Functional safety. Actually, I talked my last talk at this conference. Security also is an issue, and lifecycle management. So we'll talk about those things. Okay. So this is some of the steps. There could be variations of this flow, but this is how we see DFT in the product lifecycle. So we insert DFT, we generate high quality patterns, we do burn-in stress tests, things like those. We use AT equipment and system level testers to test it, do volume diagnosis. This is all done during manufacturing. And in the past, we would just send the chip and we'll be done with it. Not anymore. Because, and again, if you look at the information that was provided with silent data corruption errors, was that at the beginning, when devices are installed in a system, they fail. So that's test escapes. Okay. Also, some devices fail after a short period of time, which means this is early mortality things, and we have to take care of those things as well. And then we have latent defects, we have random defects, and then finally wear out. So we need some in-system test and monitoring. And it has to be much higher quality than what we used to do in the past. For example, we use logic-based. Logic-based may not be adequate for those new requirements. We have to do something a little bit more innovative. Monitoring of aging, and again, it depends on the market and depends on the technology. But we have to think ahead a couple of generations of technologies. You know, in some sense, we should be like the chess players. Whoever can foresee the larger number of steps, well, it'll most likely come up with a solution with better longevity. Okay. And believe it or not, some people are very interested in do remote diagnosis. When you operate a large data center and something fails, it may take you a couple of weeks or months to get this part to the lab and retest it. Sometimes you will never get it. That's just complexity of life and logistics. So there's interest in testing the chip, bringing the failout data, analyzing it, learning from it, updating the test, and sending updated stuff back to the other chips that are in the field. And this is not science fiction at this point. It's not far away future. The future is, as they say, is here. It's just not equally distributed. So some people see it, some people don't see it. Okay. All right. So test quality. This is very important topic today. Okay. So those of you who like physics in high school, I was one of those fascinated by physics, but eventually decided to study engineering. You know about the standard model of particle physics. There are 17 elementary particles that, at least today, the scientists believe they cannot be divided any further. And all 17 are sufficient to explain all the things that happen in the universe, electrically, magnetically, gravitationally. This is all what we need to know for now. Now, you could argue that we have more fault models, but conveniently, I selected some representation that is kind of in cardinality similar to that, just for entertainment, because you heard that entertainment was part of the fun that we need to have here. So I wanted to comply. And you can see on top, you can see combinational type of fault models. At the bottom, you see those sequential, those timing related and stuff. Okay. So now, luckily, in our case, we would like to have the smallest number of faults as possible, but have a selection that will give us good measure of quality, that'll help us in generating good quality tests, and help us in doing diagnosis. Diagnosis is very important. Okay. So looking at all of those here things on the right, I think the most promising, if you look at the last 10, 12 years, you look at all the publications with silicon data, that's important stuff. The truth is in silicon. We can speculate, but unless you test 1 million parts and actually collect the data, it's just discussion. Okay. So if you look at evidence for the last 12 years, the most effective fault models were cellular test and specifically 2-cycle cellular test. Okay. And cellular is actually implementation of a user-defined fault model. So you know of some behavior, now you just describe it and you use it as a model. It's very flexible, very flexible. So what should we do going forward? We have two options. We can think of something completely new, or we can improve something that we have already. And I would suggest that we start with something that we have and something that looks most promising. In my view, it will be, so the question is, are we there yet? Are we done? No, we are not done. We still have a lot of work to do. Now, the challenge is that this work has to be experimental, has to be done in silicon, and has to be done in large volume, which is not a trivial thing to do, because when we want to validate new approach, and we publish, including at this conference, many papers, our partner customers who actually own the silicon, they have to test 1 million parts or something like this, both the classical way and with the new fault model. And those of you who know how test flows operate, you know that logistically, that's not a trivial thing to do. So the most promising one is, in my view, is 2-cycle cellular test. Okay, and should be also timing aware. Now, the timing awareness is very important because I'll show you in a moment why it is so important. So, defect-oriented test is not a new concept. Has been around for a while, maybe like 40 years. Okay, but initially it was developed for defects that came from the fact that labs were not clean. It was essentially dirt, and this dirt resulted in some missing material. Okay, then we introduced into the modeling, we introduced like DFM rules, recommendation, guidelines, that kind of stuff. Okay, but recently the defects are very subtle because they may affect resistiveness. If you have misalignment of masks, you have to multi-patterning and things like those. There's no additional blurb of whatever dirt. It just things are shifted a little bit, and that changes resistivity. Okay, and that in some situations creates an issue. So let's talk about all creatures great and small for a change. So if you look at, just for simplicity, let's say we look at a FinFET transistor. This is a good operation. Now, there could be various types of defects. And actually, one of the key is to find what are the values of resistances. And from experimentally, this is the benefit that you get when you do high volume diagnosis and you observe how things fail. Because some of those things are very fab proprietary. But let's start with the simplest fault model, with the simplest case, where actually the transistor doesn't switch. So this like infinite delay is combinational or sequential behavior, but it's not parametric, it's not timing. Okay. Then we have gross delay. So it is something that could easily be detected by the type of transition type of fault model. And the real interesting part is small delay defects. And by small, meaning that they are there, but they're small enough, there's ambiguity. When can we detect and when we cannot detect them? And the fact, it actually depends on the environmental conditions, whether we can detect them or not. So that's actually a challenge. So timing aware cellular test actually looks at defects inside cells. And we typically do analog simulation to find out how it behaves, what is the size of the defects, and so on. And then we look at the context of the design. So we try to excite it along the longest path and propagate it along the longest path. So, and there is a defect and exceed the cycle, and then we detect it, which is nice. And actually, again, from experimental data published by partners that work with us, This is actually the most effective of the cell-aware test stuff, the 2-cycle timing-aware thing. Okay. But let's look at the design process, because we do design for test, but sometimes I feel that we don't pay enough attention how designers actually design chips. So they have to design chips so they can work under different PVT corners: process, voltage, and temperature. So the environmental conditions will be voltage and temperature, because they will change during operation. If you run some application that is very intensive in processing, may have voltage droop and stuff. Obviously, temperature also changes and so on. And there are also then the process variability for transistors and interconnect. And this is a simplified model, because for process for transistors, you could also have 2 more: slow, fast, slow, so it'll be 5. But even this, there are 135 corners. Okay. And in some cases, people may use more, some cases may use less, and so on. But then don't forget that there is another process corner that we will need to add, which is aging. So now let's look at, here we have an example of, let's say it is multi-million gate design in FinFET, okay? And if you look at now, here we have, just for simplicity, we have just 2-dimensional stuff, temperature and voltage. Now you can see that the longest path in the whole design, let's look at 1 clock domain for simplicity and stuff. Obviously, it depends on the voltage, right? So the nominal is 1, so this normalized, so we don't deal with too specific stuff, proprietary. Voltage is minimum, the delay actually increases quite a bit. Okay, when the voltage is maximum, decreases. Obvious, right? We all know this. But the knowledge that you cannot use doesn't make you wise, the same as money that you cannot spend doesn't make you rich. That's a quote from Kleiner's book on queuing theory, one of my past interests. So now, if we develop timing-aware test for 1 corner, should we be surprised that the design fails in field operation? This is what it would look like. So we develop tests for this corner, and we put this device, and the device works in the system, and voltage changes, right? It's not nominal. Under heavy load, it changes. So becomes like this. So the yellow not overlapping with blue, that's just a hypothesis. There's no trouble found. And you know the paper that ITC published many years ago. Design fails in the system, they put it on a tester, it passes on the tester. Put it in the system and fails. Well, if you test it under subset of the conditions, and then in the system you have much richer set of conditions, that's not surprise, right? So what should we do? Well, imagine that here we have 100,000 faults, actually for the design that I mentioned earlier, and we are trying to test them along the longest path, okay, under different process corners. So for nominal, we will have 27,000 patterns, okay? Let's not pay attention to the absolute number, but just the relations. So now we also want to include the remaining 8 corners. And if we include temperature minimum and voltage minimum, it looks like we will select different paths. And actually 13,000 paths will be different than the ones that we started with. So now, instead of 27, we have 40,000 patterns, okay? And if you go like this, this is the different corners. By the time you superpose them and you kind of aggregate them, you get 63,000 patterns, more than twice if you do it only for single corner. But now, what we can cover is much bigger set of conditions. I'm not saying that we'll cover everything that in real system will happen. This will never happen. We live in the real world, not ideal. But now we're coming closer. Okay. So what will happen is that if you test the design under conditions shown here in blue, you may actually not detect the error. So you say, oh, this design is okay. But in a system, if you create the condition for the red, then actually you will exceed the cycle and the design will fail. So the summary is that higher test quality may require multi-corner tests. You say, wow, so now we have difficulties in storing the patterns on a tester. Now you're saying that there'll be more. Yes, that's what I'm saying. If you want the ultimate quality. If not, then let's agree that you're not into quality, okay? But there will be good news as well. We'll also find a way to address this issue. So more patterns will be needed for high quality. Now the question is that we address the test pattern generation. The second part will be, okay, how can we now accommodate it, okay? Because, for example, the pattern count in comparison to what you're doing today will increase by 3x or 5x. This will not be doable unless we think of something else. So let's look briefly at DFT evolution. And here we'll go quickly because you're all experts, aspiring and any color that we want. So SCAN was developed to fully automate test pattern generation and help with debug, okay? Compression was developed to reduce the cost of test. And we can roughly agree that these days, about 2 orders of magnitude we can get just for test compression. You made designs that won't get that. There are some designs that people get even more. Then the next step is streaming scan network. This is SoC-level DFT, okay? And you get additional compression. Actually, if you're interested in details from or observations, experiences from a real design, there was really great talk that Dan Trock from Amazon gave at the last year ITC during the Diamond sponsor presentation. So you can just Google Best of ITC 2022 and you will find it, okay? Now, here, the data is delivered through SSN bus. Is independent of the scan shifting through the cores. So this could be done at 400 megahertz, which is substantial. There's a lot of benefits. I'm not going to talk about all of them. But the bottom line is that this is another example of technology that fits very well to existing infrastructure, doesn't require too much change, and gives tremendous benefit. And this is in the CASM model of Jeffrey Moore, is called a tornado, okay? Because if you get a lot of benefit, it doesn't cost you much. That's like tornado. So very quickly being adopted. Actually, there's even possible application for this as universal streamer to load at fast, high speed load memories and stuff. Now, the requirement was that it should be entertaining. So this is how it works, okay? So packets of data are shifted by on the SSN, and then at much lower speed, they are delivered to the cores through scan chains and so on. So now SSN works as autostrada or autoroute or autobahn, or as we call it in the US, interstate highway. You get the idea, right? Okay, great. And this actually is combined with hierarchical DFT. So here, you separate planning of the top level DFT from doing DFT at the core level. At the core level, the designer, DFT engineer can come up with the best possible configuration. And then you put all this stuff together and you do automatic retargeting and everything and so on. Okay, now what about IJTAG? So conventional IJTAG, and I know that a lot of experts here in the audience, IJTAG is kind of sequential in nature, narrow, sequential, and slow. So now you can see that the token of data travels through the, you agree with me that it's slow, right? We can move on. Why it is slow? Because it's 1 bit, maximum 100 megabits per second, limited scalability. And what you need to do is to program those various registers, like for SSN, for test compress, for OCC, logic-based, memory-based, even IJTAG, all those consume. So now think about big design. Be generous. How many bits you will need for large design? 10,000, 100,000, a million? I don't ask you to raise your hand. But this particular design is more than 10 million bits. So that's a lot of bits to shift serially, right? And you may have to reprogram this network a couple of times. So what do you need to do? Well, actually, you can send this data through what we call high bandwidth IJTAG through SSN. Now, this again, in the entertaining mechanism that we're showing here, you could be doing it much faster. How much faster? Well, SSN could be 32-bit, 64. I've seen designs with 128-bit bus. And there could 100 megahertz. So this fits very nicely into multi-die design, like 3D design. It's just you add another picture to illustrate this idea. Okay. How do you feed all these beasts that is hungry for data? Well, you need to use high-speed I/O. Now, high-speed I/O, now here's another silent, not so silent revolution coming. Structural system level test. Structural system level test is kind of the maybe not so fortunate term, because system level test is typically associated with functional test, but is much cheaper, about 50 to 100 times cheaper than traditional ATE. And you can put almost unlimited memory on it. So that's great news, okay? Because now we can also do structural tests through SLT. This will not replace the conventional ATE, but it will be done in addition. So here, if it is 100 times cheaper, then it opens up possibility, because if we don't want the 100x cheaper, we can accommodate additional patterns, still get it cheaper, and so on. Okay. So structural SLT, is it oxymoron or paradox? And this is a picture from a petrified forest, because petrified wood is like structural SLT. SLT typically is associated with functional tests. Here we're talking about structural tests. So I thought the picture somehow came to my mind that from my recent trip. So in system deterministic test, we used for in system, we used logic-based. This is what the professional community recommended. And my first attendance of this conference was in Stockholm, and I was giving actually a tutorial on logic-based, okay? A couple of years ago, 20 something. So now, logic-based still has its place, but if you look at the pros and cons between logic-based and deterministic tests, you can see that for logic-based, in terms of quality, you're limited to coverage, you're limited to the type of fault model that you can work with. So typically you can get 90% plus stacked faults. With anything time-aware, very difficult. So in-system deterministic tests, so like ATPG patterns, can give you any, for any type of fault model that ATPG supports, can give you very high coverage. But there's still place for logic-based, and because it doesn't require much memory. So that's a benefit. The last item is benefit for logic-based. So at start, turn off, and things like those, logic-based could be used. But other than that, now you can see that we could use a lot of the structures that we developed previously, like you have the SSN on the right-hand side. But now, in order to apply it in the system, you will need embedded software that will control application of those deterministic tests and some memory to store the patterns. So now, DFT, in addition to hardware, patterns, and software like EDA software, you will need embedded software on the system that will actually operate, administer, collect data, do stuff like this. Okay. So now is the essence of the summary of the silicon lifecycle management. So imagine that we have a car and it has all these structures that we talked about. Actually, these days, this will be more appropriate for data centers, but automotive is coming. So now you can test it periodically and send the data through 5G network to cloud, and then you can, if the chip dies, you can do post-mortem, you could do diagnosis, yes. Now, you can do analysis on the right-hand side, and you can actually generate new patterns knowing what is the defect sensitivity, defectivity profile. And you can send it back, you can update it. Okay, and that's the essence of, you can track those things. So I'll skip the root of trust. Let's go to summary. Okay, so I think that silicon lifecycle management will be DFT centric. And you may say, is this aspirational? No, no. When you do your homework and you analyze this, you will find that it is doable, and we are the best community to actually do it. Okay. Now, DFT will evolve. So in addition to EDA software like test pattern generation, scan insertion, you know, all this stuff, and hardware like the decompressors, memory-based, logic-based, and all this stuff, we'll have embedded software. And then on top of everything, we'll have analytics that will monitor aging, stuff like this, collect this information, and there will be with feedback. There'll be system with feedback, not an open one, with feedback. And that's the basis of learning, whether using machine learning, or expert system, or some other AI techniques, it doesn't matter, but you collect information, you learn from it, okay? So it'll be tracking from the beginning to the end with DNA of the IC and postmortem. Like if it dies, you will actually do diagnosis. In system, in field, will rely on deterministic tests. There will be improved fault models and deterministic tests, stored patterns, ATPG generated patterns. Okay. I mentioned with comprehensive analytics, and also security will be needed, hardware security to protect, because you will send this data with the system to the end user. And obviously the concern is that the end user may misuse this information, so you have to protect it as well. So that pretty much summarizes my vision of how DFT will evolve in context of silicon lifecycle.